Imagine a scenario for a moment. You've just spent months writing the perfect microservice.
Oh, the dream.
Right. The logic is flawless, the unit tests are completely green, so you deploy it into production, and like 10 minutes later, the physical server hosting your application experiences a catastrophic motherboard failure. It literally catches fire.
Yeah, that's usually how it goes.
Exactly. So the question is, does your application survive? Because if you are a developer who's stepping into the shoes of a technical architect today, that is the exact question that should be keeping you awake at night.
Oh, absolutely. It represents this massive perspective shift because a developer, they ask, does my code execute? But an architect has to ask, how does my system react when the underlying reality of the data center just constantly betrays it?
Right, because hardware fails. Network cables get unplugged, someone trips over a power cord, IP addresses shift.
Yeah, and the architecture has to anticipate that chaos. It has to mask it entirely from the end user.
Okay, let's unpack this. Because OpenShift handles that chaos through what can honestly feel like a massive, impenetrable wall of
It
abstraction.
really can.
So we're doing a deep dive into the OpenShift architecture guide today, and our mission here is to decode the system design behind all of that. We are going to break down how a unit of work is actually brought into existence, how it persists its memory when disaster strikes, and, how it communicates with the outside world through all of that noise.
I love this topic. Seeing how OpenShift specifically engineers the interactions between those core components, it's incredibly revealing.
Yeah.
It teaches you how to think about scale, not as like adding bigger and bigger servers, but as orchestrating thousands of these tiny, disposable, interchangeable parts.
Right, right. And every architecture needs a foundation, so we have to start with the birth of the application.
The very beginning.
Yeah. And the guide is absolute on this point. You do not deploy containers directly in OpenShift. You deploy a pod. But I want to push on that for a second because, a container is already an isolated environment for my code, right? So why introduce the pod at all? Why wrap a box inside another box?
Well, yeah, the container is an isolated process, sure, but applications rarely operate as just a single solitary process.
Sure.
The pod exists to provide a shared context. So let's say your main application container needs helper process, like maybe a logging agent that ships telemetry data out to some central server.
Okay, yeah, that's a super common pattern.
Right. By wrapping both of those containers inside a single pod, OpenShift guarantees that they share the exact same network namespace, the same IP address, and the same local storage volumes.
Oh, so they can just communicate over localhost.
Exactly.
Yeah.
The pod acts as this logical host for tightly coupled containers that, frankly, must live and die together.
Got it. So that makes the pod the absolute smallest deployable unit.
Yep.
And bringing that pod into existence requires this heavily coordinated workflow between the control plane, which is, the management brain of the cluster, and the worker nodes, which provide the actual physical muscle.
A heavy lifting.
Right.
Yeah.
And to map this out, as I was reading the guide, I just kept envisioning a high-end, high-volume restaurant kitchen.
Okay, a kitchen. I am really curious to see how far we can stretch that model.
Stick with me here. So think about the API server in OpenShift. The architecture guide positions it as the central management point.
Right, the absolute source of truth.
Exactly. So in our kitchen, the API server is the head chef at the pass. A user places an order, a deployment manifest. The API server receives that order, validates the syntax, authenticates the user, and writes the desired state into its ledger.
Okay, I'm with you.
But crucially, the API server doesn't actually cook the meal. It doesn't provision the CPU cycles itself.
No, not at all. The API server's primary job is state management. It just records what should exist, but it leaves the actual execution of that reality to other specialized components.
Right, so the order is logged. Now we need an expediter to look at the kitchen floor and figure out where this dish is going to be prepared.
The scheduler.
Exactly. That brings us to the scheduler. Now, the text mentions the scheduler determines the optimal node based on resource availability. But, if I'm architecting this, I know it cannot just be doing basic addition and subtraction.
No, it's way more complex than that.
Right. So what is the actual mechanism for, finding the optimal node?
What's fascinating here is the two-step algorithmic process that the scheduler runs every single time a pod needs a home. It's called filtering and scoring.
Filtering and scoring. Okay, break that down.
So it doesn't just look for empty space, During the filtering phase, the scheduler aggressively eliminates worker nodes that simply cannot run the pod.
So it's just throwing out the bad options right away.
Exactly. If your pod demands, say, 4 gigabytes of memory, any node with only 2 gigabytes available is immediately disqualified. Done.
Makes sense.
Or if you placed a specific constraint like, this database pod absolutely must run on a node with SSD storage, the scheduler just filters out all the nodes with spinning hard drives.
Okay.
Welcome to SGITMystr, your ultimate destination for futuristic technology and AI innovation.